48 light-years away, in the pitch-black void of the constellation Cetus, a frozen titan hangs motionless in perpetual twilight, wrapped in a thin, shimmering veil of gas that scientists once believed could not possibly exist. For more than 3 decades, astronomers searching the vast cosmos for habitable worlds have endured a relentless series of bitter and exhausting disappointments. Time after time, promising rocky planets orbiting distant stars were found to have been stripped completely bare by ferocious stellar radiation, leaving behind nothing but scorched, airless cinders drifting silently through the freezing vacuum of space. But in July 2026, a historic announcement shattered the quiet resignation of astrophysicists around the world. Using the ultra-sensitive infrared spectrograph on the Magellan Clay telescope in Chile, together with deep observational data from the James Webb Space Telescope, international research teams detected something extraordinary escaping from the super-Earth known as LHS 1140b. It was a faint atomic signature of helium gas escaping rapidly into the vast vacuum of space, providing compelling evidence that this distant world has retained a primary atmosphere. This is not merely another routine astronomical discovery. It represents one of the most significant milestones in exoplanet research since the detection of the first planet beyond our solar system. For the first time in human history, scientists may have confirmed that a rocky planet located within the conservative habitable zone of a quiet red dwarf star survived intense stellar winds and maintained a protective gaseous envelope across vast stretches of cosmic time. Yet, as astronomers turn humanity's most powerful instruments toward this distant sphere, a profound mystery deepens. How could a planet orbiting so close to its star preserve a volatile-rich atmosphere for billions of years? What lies hidden beneath its perpetual, heavy clouds? Could LHS 1140b be the first known world where liquid oceans churn beneath a crimson sky, or is it merely a deceptive cosmic trap? To understand why this discovery electrified astronomers worldwide, one must first appreciate the formidable odds against habitability around red dwarf stars throughout the Milky Way. M-dwarf stars account for more than 70% of all stars, making them the most common stellar hosts in the galaxy. However, during their chaotic juvenile phases, which can last for millions of years, these dwarf stars emit violent bursts of radiation and powerful ultraviolet flares that can strip away planetary atmospheres. Scientists had begun to fear that planets orbiting red dwarfs might be perpetually barren, airless, and completely lifeless worlds. LHS 1140b challenges that assumption, suggesting that, under the right physical conditions, a rocky world can preserve its atmospheric shield and protect its surface from lethal cosmic erosion for more than 5 billion years. This unprecedented breakthrough provides astrophysicists with a natural laboratory in which to study how atmospheres survive near active stars. Astronomers around the globe are watching the planet closely as new spectroscopic measurements arrive from space-based observatories. Initial photometric observations indicate that its exosphere may extend thousands of kilometers into deep space. Detailed modeling of the atmospheric transmission spectrum also suggests the possible presence of a significant high-altitude water vapor haze. The survival of this protective gaseous layer opens new possibilities for studying long-term planetary habitability under intense stellar pressure. To understand the surreal nature of LHS 1140b, one must first grasp its immense physical scale, extreme density, and unusual orbital mechanics. Floating nearly 300 trillion miles from Earth, this massive super-Earth has a diameter approximately 1.7 times that of our planet, while containing about 5.6 times Earth's mass. Because of its enormous mass and high density, the surface gravity on LHS 1140b may be nearly twice as strong as gravity on Earth, but its immense physical weight is only the beginning of its terrifying strangeness. LHS 1140b orbits an ancient dwarf star at such a close distance that a complete year lasts only 24 Earth days. At this extreme proximity, immense tidal forces have likely locked the planet into permanent synchronous rotation. One hemisphere of LHS 1140b remains in continuous daylight, staring endlessly toward its sun, while the opposite hemisphere is entombed in eternal darkness. This extreme gravitational lock creates a divided world, giving rise to what astrophysicists call an eyeball planet. Imagine a world where half the globe is frozen beneath glaciers of ice and solid nitrogen thousands of feet thick. Directly beneath the warm substellar point, however, intense stellar radiation heats the surface, melts the glacial crust, and forms a colossal liquid ocean surrounded by ice. Viewed from deep space, the planet might resemble a giant, glowing eye gazing blankly into the void. Furthermore, planetary structure models derived from precise measurements of its mass and radius suggest that LHS 1140b may not be composed primarily of rock. Instead, as much as 20% of its total mass could consist of water in the form of ice and liquid oceans, making it a potentially water-rich ocean world. If all the ice on LHS 1140b were to melt, the planet could become a deep, global ocean world, submerging any rocky landmasses beneath vast alien seas. This unique structural architecture places the planet within a rare category of water-rich super-Earths. Scientists are constructing dynamic models of the planet's internal structure to estimate its precise rate of heat generation. These simulations suggest that massive plumes of thermal convection may rise from the iron core and travel upward through the mantle. High-resolution gravitational models may also reveal dense metallic concentrations embedded deep within the planet's lower mantle. Thermal energy left over from primordial accretion could still be warming the planetary interior beneath the ice shell. Geophysical models further suggest that the boundary between the rocky interior and the liquid ocean may experience powerful tidal flexing. The existence of a persistent dense atmosphere on an eyeball world such as LHS 1140b challenges conventional models of atmospheric erosion. Red dwarf stars are notoriously turbulent hosts, frequently unleashing coronal mass ejections and stellar flares capable of evaporating planetary atmospheres in relatively short periods. Yet LHS 1140b appears to have retained its atmosphere through nearly 5 billion years of stellar evolution. The crucial scientific evidence uncovered by researchers lies in the observed signature of atmospheric escape. As energetic stellar photons strike the upper exosphere, helium atoms become thermally excited and escape into space, potentially creating a vast, glowing tail trailing behind the planet like that of a comet. By calculating the rate at which helium is lost, astrophysicists may be able to determine whether LHS 1140b possesses a dense atmosphere dominated by nitrogen and carbon dioxide, acting as an enormous protective thermal blanket. Such an atmospheric envelope could perform a remarkable thermodynamic function. Global wind patterns might efficiently redistribute heat from the star-scorched day side to the frozen night side, preventing atmospheric gases from condensing and freezing onto the surface. The atmosphere of LHS 1140b could therefore be highly dynamic, protecting the surface from cosmic radiation while maintaining the delicate thermodynamic balance required for liquid water. Theoretical climate models demonstrate that without a dense greenhouse atmosphere, the extreme temperature difference between the day and night hemispheres could cause the atmosphere to freeze solid on the night side. A circulating nitrogen-rich atmosphere could act as a planetary radiator, smoothing out temperature extremes and maintaining an open ocean near the substellar region, where temperatures might remain comfortably above the freezing point. This balance of atmospheric dynamics highlights the potential resilience of the planet's climate. Computational fluid dynamics simulations suggest that high-altitude jet streams could circle the planet, carrying enormous thermal currents across the terminator line between day and night. Recent transit spectroscopy measurements may also indicate significant cloud cover floating above the substellar ocean in the upper atmosphere. Sophisticated radiative transfer calculations suggest that carbon dioxide could trap enough heat to keep this ocean in a liquid state. Stable atmospheric circulation patterns could create continuous convective wind systems that regulate the planet's surface temperature over geological timescales. Stepping onto the alien surface of LHS 1140b would mean entering a surreal landscape unlike anything imagined in science fiction. Standing on the shoreline of the central substellar ocean, an observer would see the host star dominating the sky. It might appear several times larger than the sun does from Earth, hanging motionless at the position of eternal high noon, never rising and never setting, because there would be no traditional day and night cycle. Weather patterns would be driven by permanent temperature gradients. Superheated air at the substellar point would rise violently and rush toward the freezing night side. There it would cool, sink, and flow back toward the ocean as powerful surface winds. Along the boundary between light and darkness, raging squalls and torrential rain could batter cliffs towering hundreds of feet above the alien ocean. Advanced computer simulations suggest that the central ocean could span thousands of miles and reach depths of up to 100 kilometers. Beneath this warm, liquid sea, immense hydrostatic pressure combined with internal geothermal heating generated by tidal flexing could power active networks of hydrothermal vents on the seafloor. These vents might release mineral-rich fluids into the dark abyssal waters, providing energy for potential marine life. Conditions around these deep-sea vents could resemble hydrothermal environments found in Earth's oceans, such as the Lost City hydrothermal field. On Earth, mineral-rich hydrothermal vents may have served as cradles for primordial life billions of years ago. On LHS 1140b, similar geothermal systems could sustain complex chemosynthetic ecosystems that survive independently of sunlight in the dark depths beneath an alien ocean. Such deep-sea hydrothermal networks could maintain stable ecological niches, protecting life from violent surface weather and stellar flares. Organic molecules dissolved in mineral-rich water could react continuously at high-pressure vent sites. Geochemical reactions between seawater and basalt on the ocean floor could generate a steady supply of molecular hydrogen, providing a continuous source of chemical energy. Tidal flexing induced by the gravity of the host star could pump energy into the deep seabed, sustaining volcanic activity over immense periods. Submarine hydrothermal plumes could circulate vital nutrients throughout the deep ocean basin, potentially supporting microbial forms of life. The detection of an atmosphere surrounding LHS 1140b could mark the beginning of a revolutionary era in astrobiology. International research teams are scheduling transit spectroscopy observations with the NIRSPEC and MIRI instruments aboard the James Webb Space Telescope. Scientists are actively searching for important atmospheric biosignatures, including molecular oxygen, ozone, methane, and dimethyl sulfide, a chemical compound produced on Earth by marine phytoplankton. If future spectroscopic observations reveal that these chemical species coexist in a state of chemical disequilibrium beyond our solar system, the results could provide compelling evidence of biological activity. But even if LHS 1140b proves to be barren, its scientific legacy could permanently reshape our understanding of planetary habitability. It may provide evidence that small, rocky worlds orbiting M-dwarf stars, which make up the majority of stars in the galaxy, can maintain atmospheres and preserve liquid oceans over long periods. LHS 1140b stands as a beacon, demonstrating that our galaxy may contain countless ocean worlds. As humanity's telescopes look deeper into the cosmos, we move closer to answering our oldest question: are we truly alone in the universe? The discovery of LHS 1140b transforms the search for extraterrestrial life from an abstract probability into an immediate and testable scientific reality. Within the next decade, as next-generation observatories join the James Webb Space Telescope in analyzing distant atmospheres, humanity may catch its first glimpse of an alien biosphere, forever altering our place in the cosmic story. This world serves as an inspiring reminder of how much remains hidden within the quiet depths of the universe. Future space missions may continuously monitor the planet, mapping its atmospheric absorption lines in extraordinary detail. Humanity stands at the threshold of a new universe. The exploration of distant, potentially habitable worlds has officially begun. Observational astronomy is entering an unprecedented golden age of discovery, unveiling the secrets of life across interstellar space. Astronomers now look forward to decoding the spectral messages hidden within the glowing atmospheric rim of LHS 1140b.